Algebra?
Yeah, sure.
So where were we on Friday?
Rational roots test.
We did have the rational roots test. Well, I told you the rational roots test, but we'll actually use it today. So I want to do some more examples. Of characteristic polynomials. And finding eigenvalues. And then we're going to try to put this stuff into some sort of conceptual framework. Alright, so we did several 2x2s and one 3x3. I have some more 3x3s to throw your way. This one should be pretty easy. Zero, negative 1, 2. It should be pretty easy unless there's a typo. And then I'm in trouble. Okay, lots of zeros. That should make your heart happy. So how do we find the characteristic polynomial, the eigenvalues?
Just
the eigenvectors.
tack a little minus t on it and take the determinant.
Do I tag them everywhere?
No, on the main diagonal.
Thank you.
And then expanding cofactors along the bottom row.
That would be the intelligent way to do it, right? With those zeros, the best thing to do is expanding cofactors along the bottom row, exactly as Daniel said. So it's going to be positive because 3 plus 3 is even or something. 1 minus t times this determinant, right? So we get t squared minus 3t plus 2. Any ideas?
You can factor t minus 2, t minus 1.
So in fact, if I pull out a negative here just because I like to have my t's in front, this would be t minus 1, and this is a t minus 1, t minus 2. So what are the eigenvalues?
1 and 2.
So the eigenvalues are 1 appearing twice in the list and 2. Okay. Undaunted, we proceed. So let's look at the eigenspace for 2 first. Anybody can do it by inspection? I don't think I can. Can you just look at that? I can't do it. So I want the null space of what I get when I subtract 2 times the identity. Something's wrong. I made a mistake somewhere. There's the mistake. Thank you.
Where was it? Sorry.
It's a negative thing.
Okay, thanks.
So, how do we find the null space? We do echelon form. Well, look, let's save ourselves a little trouble here and realize that we're going to have a pivot in the third column, which then can clear out above it. Right? Mm-hmm. And then I've noticed that I have 2 rows that are the same. Now that we've caught the typo. So I'll have a 2, 1, 0, 0, 0, 0, 0, 0, 1. That's not reduced echelon form yet. Right? To be in reduced echelon form, just to remind you, the row of zeros has to be at the bottom. Isn't that 0, 0, 1. 1, 1 half, 0 if you insist on reduced echelon form. You don't really have to do that at this point. So what's the dimension of the null space? What's the dimension?
2.
One basis vector, 1.
Okay. Say something else.
And what's the basis? Well, the third vector, the third component is 0. And minus 1/2, 1. If you insist on using our algorithms, but I would rather use integers if you don't mind, so I'm just going to write it as -1, 2, 0. And that would have been obvious from this. Right, when you rotate this 90 degrees.
You can also see it from the first.
Once you know that goes away.
It was the first two columns and 0 in the third.
Huh?
The first two columns in the matrix was 0 in the third component.
You're saying because you know this would be exactly one row.
Right, I'm lost. What am I seeing? Okay. What about eigenspace for 1?
What does it mean when there's one is like a twice?
Double root.
Yeah. It's somewhere like the.
Well, it means it's a double root of the characteristic polynomial. Now we're going to try to, that's what I'm talking about today. What does it mean? So what do I get when I subtract 1 times the identity?
You get 1 0.
I don't see anything yet. All these.
It's a third.
I
You
usually
down
do.
the matrix.
Oh,
It's
I
2,
got a
2,
row of zeros. Okay. Second row.
2, 2, 2, 4.
Oh gosh. Okay.
So you turn
So you do cofactor, right?
No.
It's rank 1.
No, it's fine.
Rank 0.
You
No,
Rank
rank 1. Sorry, rank 1.
So this has rank 1 because the second row is a scalar multiple of the first row. So what's the dimension of the null space? 2. So there's a little aha here. The dimension of the eigenspace is 2, which is exciting actually, because that means I will have 2 vectors linearly dependent here, and presumably this guy will be linearly dependent added to those 2, and I'll have a basis for R3. So let's see, what's the basis for the null space of this guy?
One.
Now, is it obvious that this guy put together with those form a linearly independent set?
Yes, it's completely obvious.
I mean,
Jonathan?
yes, it is.
Why is it completely obvious, Jonathan?
Well, the third one,
Karen seems
because
to
of where the
think
zeros are, is obviously independent from the first 2.
There's no linear combination of these that gives that.
Right? And then the first 2 are linearly independent.
Those are linearly independent in the xy plane, in the x1, x2 plane. This guy's not in the x1, x2 plane.
But it's
Right.
not.
So by the
That's
thing
it.
we proved at the very beginning of our discussion of linear independence, we're done. Right? We have a plane with 2 linearly independent vectors there, and the third vector is not in the plane. That means they're linearly independent. Thank you to Jackson for remembering, even if the rest of you were sitting mute. So what does this mean? I have a basis, and if I take script B to be this basis, what's the linear map matrix with respect to that basis?
So you just take those 3.
With respect to this basis, what is T doing? What's it doing to the first basis vector? It's sending it to what? Where did that first basis vector come from? So it goes to, so T of this vector is twice it, plus 0 of each of the others. Remember what this means, right? You're representing what the linear map does to the basis vectors in terms of the basis vectors. What does it do to these guys?
Keep where it is.
So what do I put here?
0, 1, 0, 0, 0, 1.
Very good. So it's diagonal. Cool. On to the second board. 2. B is not such a pretty matrix. -2, -2, 5, 0, 2, -1, -2, -1, 4. Characteristic polynomial, please.
-2 minus b.
Why don't we write out the matrix we're gonna,
I am at the end of this discussion going to see if we have a shorter cut for doing this. -2,
Wait,
-1, 4 minus 2.
After WebWork, don't we know a shortcut for this?
Hmm?
After WebWork, don't we know a shortcut for this?
Say again?
After WebWork, don't we know a shortcut for
Do
this?
you? For 3 by 3?
Oh, no, is it just for 2 by 2s?
You know a shortcut for 2 by 2s, but we're going to try to generalize it. We'll get there. We'll get there. All right, what do I do with this mess?
Cofactor in the first one.
That would seem intelligent, right? Cofactors on the first column.
If you
So-
don't have any zeros, what would you recommend?
Just go for it.
Okay.
So you're gonna use the mess.
All right, so negative, I'm going to factor out t plus 2 times the determinant 2 minus t, -1, -1, 4 minus t, plus -1 times 0 times stuff, plus -2 times what determinant?
-2, 5, 2 minus t.
All right, crank for me.
The second.
What do I get here?
You get t squared minus 16.
T squared minus 16, no, plus 8
7.
minus 1.
So you would recommend expanding those? Like we're doing?
Yeah, that we have to, because otherwise, yeah, we have to simplify the
Yeah.
quadratic
sum,
part,
yeah.
and then we have to figure out what this is. Minus twice 2 minus 10
Plus
plus 5t. Oh, I was afraid of this. Well, I hope I don't have a typo on my paper. This will be very annoying if I do. So, there's no way to factor this, and this has nothing nice going for it. So what do I got to do now?
Rational roots thing?
Multiply it out.
I gotta multiply it out.
Yeah. Brute force, let's do it.
I've gotta multiply it out, simplify, and then see if I can factor what's left.
Alright, I'll do the second. I'll do the second.
Thanks. So negative, what have I got? T cubed
Minus
plus
16.
2t squared minus 6t squared plus
17.
7t minus 12t plus 14. And since I have the negative factored out, I'll keep going.
10t minus.
Here more.
All right. Undaunted, we continue. How many t squareds? Well, I can do that part.
5t.
Minus 5t
Plus 2.
Plus 5.
Plus 5t.
plus 5t.
Yeah.
And then minus 2.
Do you want to calculate it?
No, I don't want a calculator.
They can factor. You can.
So, rational roots test the leading coefficient is plus or minus 1, so any rational root must be an integer. Remember, I told you last time that the numerator of your rational root would divide this, and the denominator would divide the coefficient of the leading term. 1 doesn't have very many factors. So any rational root must be an integer, and that integer must be a factor of the constant term. So you say to yourself, what integers divide negative 2?
Plus or minus 1, plus or minus 2.
What would you see as
So, it's like 4 whole numbers?
Well, we don't, all we have to do is find 1, so let's start with 1.
Yeah.
Is it a root?
Yes.
1 minus 4 plus 5 minus 2.
Goes to 0, checks out.
Looks like a root. Aha! 1 is a root. So, some of you probably know synthetic division.
Yeah.
I don't. I learned it once teaching pre-calculus years ago, but I never remember it. So what I would do is I would say 1's a root, therefore t minus 1 has to be a factor of this thing. If you guys know synthetic division, you know a shortcut supposedly for doing this. It's really the same thing except you save writing t's. So how many people remember that they learned how to divide polynomials at some point?
I can do that. It isn't I learned it back.
So how many t's go into t cubed? Approximately t squared of them. You do it just like long division with integers. Right? Then I get minus 3t squared, so I get minus 3t here, minus 3t squared, bring down the 5t. Subtract, bring down the negative 2. Oh, isn't that lovely? It goes evenly like it was supposed to. And now you easily factor this. I've got a minus, a t minus 1, and what are the factors of this?
T minus 2, t minus 1.
Isn't that coincidental? Same characteristic polynomial as this matrix. And yet it looks so different. So eigenvalues are 1, 1, and 2 yet again. At which Ted heaves a sigh of relief that he didn't screw that up, copying it to his paper. Hmm? Probably not. So let's see. Let's start with E of 2. Null space of negative 4, negative 2, negative 5, 0, 0, negative 1, negative 2, negative 1, 2. Once again, I have a 1 there. And once again, these guys are multiples of the same thing. But actually, it does have the same eigenvector, doesn't it? Well, sort of made it up that way. So, basis for E of 2 is the same vector we had earlier. Who knew?
Sorry, you may have said this, but if we have a repeated eigenvector, should we
Repeated
expect
eigenvalues.
eigenvalue? Should we expect dimensions?
Gosh, you people, be patient. E of 1, null space of. Well, what matrix?
Subtract 1 from the diagonal.
Well,
Minus negative 3, 5, 0, 1, minus 1, minus 2, minus 1.
oh, lovely. Couldn't you give me anything nicer than this?
That's pretty nice.
No, it doesn't look nice to me.
Okay, you add the negative over the bottom to the top.
Okay. And then take the negative of that. So if I add negative this to this, to get a 1, right? The negative of the first row to the third row, and put that here. 1, 1, -2, 0, 1, -1. And now if I use this guy to kill off the -2, I get aha. Woo. Well,
How convenient.
so I do have a row of zeros, but what are you noticing, Gabe, to answer your own question?
That's,
What's the rank of this matrix?
Well, 2.
So what's the dimension of the null space going to be? 1. I believe that's the correct.
Yeah, that's back up. So you're right.
So, so a basis for the one eigenspace is the vector one free variable.
1, 1, 1.
1, 1, 1, yeah.
Let's just check to be sure. If we multiply by 1, 1, 1, what do we get? Well, if we multiply by 1, 1, 1, you're adding the columns. So you get 1, 1, 1. Yes!
Is that total coincidence that it's the sum of the two basis vectors from the other?
It's how I made the problem up. Okay, so why are you upset, Gabe?
well, personally, I feel like if one eigenvalue is doing twice the work, it should probably have twice the eigenvectors as a reward.
And yet it doesn't.
It doesn't. It's not fair.
So
Life isn't fair.
Math is not fair.
So what are we noticing? We're noticing that the dimension of the one eigenspace is only 1, yet the multiplicity with which lambda was 2. So we're going to have words for these things. I might as well teach you the words now. The number of times 1 appears as a root is called the algebraic multiplicity. Namely, it's the exponent that appears when you factor as a product of linear factors.
So the number of basis vectors is the geometric one?
This is called the geometric multiplicity because it's telling you the dimension of something geometric, namely the eigenspace.
Are these terms only used in discussion like eigenvalues and eigenvectors, or is it?
Yes.
Okay.
Is the geometric multiplicity less than or equal to the algebraic multiplicity always?
Yes. So we will actually prove that. If not today, we'll prove it Wednesday. So Cameron's question, if you didn't hear it, was, is this coincidence that the two numbers were equal here and the geometric multiplicity was less here? And in fact, we'll prove a theorem soon that the geometric multiplicity is always at most the algebraic. So, is this matrix B diagonalizable? A was, right? We got the diagonal matrix for it.
Yeah.
What about
Yes.
B?
yes,
Why yes?
because can't we could put like 1, 1, 1 in twice to our.
Will that be a basis?
No. No.
No. So
I
no, you
feel like you
can't.
need to have 3 distinct ones for some reason.
Not distinct, what do you mean?
Well, 3
Linear
linearly.
dependent. So, well, maybe there's another eigenvalue we missed somewhere that gives us another eigenvector.
Is it called?
Wait, could there be? Didn't we just factor P of t? Could there be any hidden roots? No, there couldn't be. So the only roots are 1 and 2. Maybe 2 had another eigenvector it could have contributed for us. No.
Theorem.
Cameron's theorem says I had algebraic multiplicity 2, so there could only be one linear independent eigenvector for this eigenvalue. We only had one for this, so we cannot find a basis consisting of eigenvectors. Yes, sir?
What if you just threw in a 0, 0, 0 as your last column?
That's as bad as what they said.
It's worse.
If the 0 vector is in a list of vectors, can that list be linearly independent?
No.
Not as your last basis, as your last column in your.
But that has to come from doing a, wait. The last column of what?
Of your matrix, your diagonal.
No, but it has to, you have to have a basis. We don't have a basis consisting of other
Cross the two that we have.
Hmm?
Take the cross products two we have.
Yeah, but that'll just give you some random vector, and what will T do to it? What will the matrix do to it? Something random. It won't. See, to have a diagonal matrix, remember we started with this the other day, to end up with a diagonal matrix, you have to have a basis consisting of eigenvectors.
So
That's what it means for the matrix to be diagonal.
So does this mean it's hard to tell what B does?
It's, well, actually, it's not so hard, and if you pay attention to homework you're doing over the next week or so, you'll have a good clue. And we'll talk about this some more.
B is not diagonal? Diagonalizable.
It is not.
Or we're saying that the T of B cannot be diagonal? Is that equivalent?
Right, the matrix represents a linear map. That linear map is not diagonalizable. Right. All right, so I want to make a couple of comments here. One is, now that we have this polynomial written out, could we have gotten there some other way? We were lucky for this one. It came pre-factored, basically. This one we weren't so lucky.
Well, no.
We just like
I
start
was
with
gonna say, if we hadn't been lucky with the other one, we could have used what we had used before, because it would have been the same, but what that would do, we would have to do with the first.
I mean, there's no way to, I just made these matrices up. There's no way to have known that they would end up with the same
Is
characteristic
there
polynomial.
any way to kind of use the trace thing with the cofactor idea?
All right, so I think Reese is on to something. So what do the coefficients of P of T mean? So we already know. So what was the shortcut for the quadratics, for the 2x2s that you noticed?
T squared
T squared
minus
minus
trace T.
plus.
So we'd already said what this guy had to be. Remember, we said that from the definition. We had this on the board last time. The characteristic polynomial was determinant of A minus T times the identity. The constant term is what you get when you put in T equals 0. When you put in T equals 0, you get the determinant. So that one wasn't a surprise. But what you're noticing here is that this coefficient is the trace, the sum of the diagonals.
Shouldn't it be A minus T?
Oh, shoot.
Yeah.
Thank you.
What would you want?
Yeah, sorry about that. All right. So this is actually interesting already. Because what does this tell you?
That.
Tells you the product of the eigenvalues is the determinant, and the sum of the eigenvalues is the trace. Now that's not so surprising, because remember I told you, if you can diagonalize A, then the characteristic polynomial is the same. Well, the trace is the sum of the diagonals, that's the sum of the eigenvalues. The determinant is the product of the diagonals, that's the product of the eigenvalues. So this isn't so surprising.
Is that fact to do with the eigenvalues?
Say again?
Is that fact to do with the eigenvalues? The sum is the base of the...
Yeah. So if you had 3 by 3, you should be able to get, so you have a minus t cubed plus some number of somethings t squared plus some number of somethings t, and we do know that we still get the determinant as the constant term. So I'm actually going to put a minus here. Where do you think the trace is going to come?
After the left.
So this is still going to be the trace. Because if it's still going to be the case that if we could diagonalize A, the characteristic polynomial of A is the characteristic polynomial of the diagonal matrix, and for the diagonal matrix, if you take this minus t times the identity, you're going to get lambda 1 minus t times lambda 2 minus t times lambda 3 minus t, which is minus t cubed. No, just get this one. Minus t cubed. How do we get a t squared? Well, if you're going to get a t squared, so you lied, I think. Didn't you? We'll see. What if I take t squared? What am I going to get? T squared will have a lambda 3.
You get the sum of
T squared will have a lambda 1. So I'll have the sum of the lambdas times t squared. Minus, what's the coefficient of t? How do I get a t? Well, I get a lambda 2, lambda 3. I get a lambda 1, lambda 2, and I get a lambda 1, lambda 3, all with minuses. So this is interesting. You're getting pairs of products of the eigenvalues. And then finally you get lambda 1, lambda 2, lambda 3 as the constant term. So the trace is going to be this guy. Now, what in the world is this coefficient? And some number of books ago, I called this guy Fred. So who's Fred?
He's the sum of the permutations of two.
So this is Fred.
And I guess the trace is the sum of the permutations of 1.
And the determinant
But
is the sum of
the question is, if you look at your original matrix, how do you compute Fred? So let's check for our example here that these coefficients are matching. If the diagonal,
You erased the first
what in the world?
Well,
What was the trace of our diagonal thing?
the original one?
What were the eigenvalues? Sorry, what are the sum of the eigenvalues? 1, 1, and 2. It's 4, which is right. Remember, there's a minus factored out of that thing. Determinant was 2, product of the eigenvalues. And if you took the pairs of products, 1 times 1, 1 times 2, 1 times 2, you get 5, which is what we have.
Thanks, Brad.
The question is, how could we, so you know how to read off the trace, and you know how to do the determinant. How do you see Fred from the original? What is Fred
I'm looking at B.
By looking at the matrix or
in the original, from the original matrix, right? If you actually think about where you get a t term, when you expand that determinant, you will convince yourself, I'm not going to take the time to go through it super carefully. You're going to take the sum of the 2 by 2 determinants, or the 2 by 2 cofactors, along the diagonal. So if I looked at my original matrix, and took the 2 by 2 cofactors along the diagonal, I would have this 2 by 2 determinant. What do I get? I would have this. Seven.
Yeah.
And then the one that's harder to draw
Is the 4 corners?
is the 4 corners. Is the one where you cross off the middle guy. You would have, so you cross off here and you get -8 plus 10.
That's Fred.
So that's how you see Fred.
Where did Fred come from?
We're just working it out.
Iowa. If you actually go to figure out how do you get a t coefficient.
I'm sorry, I meant where the name came from.
Oh, I was teaching linear algebra 20 years ago and somebody called it Fred, so I've used it. Okay. So, alright, that's where the characteristic polynomial comes from, and if you have a horrendous one, you have a way of double checking your calculation using what we've just talked about here. Alright, so we have some theorems coming up. Cameron's already anticipated one of them, but I want to do the more basic one today, and we'll come back to this on Wednesday. True or false? If all the eigenvalues were distinct, if there were no repetitions, we would be in good shape. We would always have a basis of eigenvectors.
Are they rational?
Doesn't matter.
And we have shown that
But say real.
Yeah.
we have shown distinct eigenvalues produce linearly independent eigenvectors.
No, we haven't. That was in fact where I was leading. So I gave.
No. This is the second time today, so
Second time today.
with
Getting
the two.
Oh yeah, right. Theorem. Suppose lambda 1 to lambda k are distinct eigenvalues of t, or matrix A, I don't care. So what does distinct mean?
Different.
They're all different numbers. And let's suppose that v1 to vk are corresponding eigenvectors. So by corresponding, I mean that v3 is an eigenvector with eigenvalue lambda 3, etc.
When we were talking the other day, when we were walking through, we said that corresponding eigenvectors must exist. But we don't have, do we have a formal proof for that, or is that just kind of like?
No, it's from the definition.
Okay.
Eigenvalue was a lambda for which t minus lambda I was singular.
Oh, and
So there is a null space, so there's at least one dimension's worth of non-zero vectors.
Okay.
Okay? So the statement is going to be then v1 to vk form a linearly independent set. And since I know Jonathan wants to put an appropriate annotation in his notes, this is important. I.e.,
Exam.
well, not tomorrow, but, yep,
Oh my God, we just start worrying about the final, don't we?
Well, last night.
Finals 2 weeks from Wednesday, correct?
yes.
Jeez.
All right, before the blubbering takes over the class. How do we prove a set of vectors is linearly independent?
Declaration of independence.
Alright, stated.
Suppose suppose C1V1 plus plus DKVK equals 0. We must now show C1 equals ... equals CK equals 0.
You want to show the only linear combination of the vectors that gives you the zero vector is the triangle. Now, I'm actually going to, because I let Dave feel good saying all that, but I'm not going to actually use it directly. You'll see it's a little sneaky because you're used to just saying, writing down the declaration of linear independence and then taking t of both sides and seeing what happens. And then it turns out to be, we're going to do something like that, but I'm going to set it up slightly differently. And so Gabe will not, it won't be totally wasted. All right, proof. If k is 1, what's true? If we have just one eigenvalue,
You have one eigenvector.
you have one eigenvector, and what do you know about that vector?
It's
Linearly independent, right? It's a non-zero vector. So if k equals 1, we're done. Ooh. Similarly, all right, so now let's here's the sneaky proof. And you don't have to do it this way, but it's the easiest way to do it. Let j be the number, be the largest number between 1 and k, integer of course, before some wise person. Let j be the largest integer between 1 and k so that v1 to vj are linearly independent. So I win if
J equals K.
we're done if j equals k. So let's suppose j is less than k. What does that mean?
That means if you add the j plus 1 vector, they become linearly dependent.
So this means the first j are linearly independent, but if we add in j plus 1, it becomes linearly dependent.
The j plus 1 vector is sum of.
Right. So the variant of Gabe's declaration is exactly what Ken's saying. How can it happen? This is back to actually what Jackson was remembering earlier today. How can it happen that you have a linearly independent set, but when you add another vector, it becomes a linearly dependent set? What must be true?
You can write that as
Linear
the
combination
sum of.
yeah. Didn't we prove that?
Yeah, that was one of our proofs.
Yeah.
I remember because I memorized it from the test and it wasn't long.
Well, you get to use it now, Jonathan. So thus, vj plus 1 can be written as a linear combination of v1 through vj with some scalars. Now, what should I use about vj plus 1?
It's non-zero.
But it's an
Eigenvector.
it's an eigenvector. So if I take t minus lambda j plus 1 times the identity, what happens when I multiply by vj plus 1?
Give you multiple features.
No. Gives me what? What's t of vj plus 1?
vj plus 1.
Times.
Lambda j.
So if I subtract lambda j plus 1, I have
0.
0. This is our way of finding the eigenvectors, right? You do the null space of A minus lambda I. So I'm going to apply t minus lambda j plus 1 times the identity to the whole right-hand side. Now the scalars will pull out. What's t of v1?
It'll be lambda by v1, right?
And then what's lambda j plus 1 times the identity times v1? It'll be lambda j plus 1 times v1. So do you agree that I get this quantity? Plus, I'm not done yet. But t of v1 is lambda 1 v1 minus the scalar multiple of the identity v1 is that scalar times v1. Factoring out, I have the scalar that pulled out, the difference of the lambdas, and I get that for every one of these terms with the corresponding difference of eigenvalues. Does Does everyone agree? So I have 0 equals, and that's so important I'm going to box it. Why are we done?
That's coefficient.
Well, not quite, but what go on. How can you have a linear combination of v1 to vj that gives you the 0 vector?
They have to be linearly dependent, but they're not.
No, not so fast.
All those coefficients have to be 0. Yeah.
Because the v1 to vj are linearly independent, I know that all the scalars appearing here have to be 0. So,
But all the eigenvalues are distinct.
so all the eigenvalues are distinct. All of these are 0. But, as you guys just said, these quantities are all
Non-zero, so that means all
The
the C's are 0.
Right.
That means it's linear.
so therefore all the C's are 0. What's wrong?
That's linear.
What's wrong?
All the C's
Come on guys, you have 30 seconds.
Therefore, vj plus 1 are equal to the vector would be 0.
Right. Yes. Well, finish it, Mr. Showoff. Why is that no good?
Because then
Because the eigenvector which is non-zero by definition.
Eigenvectors cannot be
they're
contradicting definition of eigenvector. Therefore, this can't happen. So the supposed j is less than k can't happen, which means we're done. Okay. So after the test tomorrow, we'll go back and discuss geometric algebraic multiplicity stuff. And